Some properties of gases are they compress easily. Because they're so far apart, you can compress them because there's a lot of space between them. They mix completely with other gases, so if I put a couple of gases in the same container, they'll mix completely. They exert pressure on their surroundings, and they take the shape and volume of the container that they're in. Gases behave according to the kinetic molecular theory. The first part of that says that the volume of individual gas particles can be assumed to be zero because they're so small in comparison to the container that they're in. But this is not completely true because gases are matter, therefore they have mass and they take up space. So know that that one isn't true, and so in a few minutes when we talk about real gases, this will come into play. Particles are in constant motion. So that is true of gases, as are solids, liquids, and gases. Everything is in constant motion. Just gases move more than a liquid or solid would. We say that the gas particles are not attracted or repelled by each other. But in reality, if they have a strong attraction, they may actually have some attraction or repulsion. So that one also isn't true, even though we're going to make that assumption to make the problems easier in the equations. And finally, number 4, people forget about a lot of times, but the average kinetic energy of a gas is directly proportional to the Kelvin temperature of the gas. So the higher the Kelvin temperature, the higher the kinetic energy. If I double the Kelvin temperature, I'll double the kinetic energy. But that only works for Kelvin. If it's Celsius, if I double Celsius, the kinetic energy will increase, but it won't double. So real gases. We assume KMT to be true, again to simplify our equations. But real gases, that ideal gas model is going to fail under high pressure and low temperature. So gases are always going to be most ideal under low pressure and high temperature. We said in first year chemistry that you can remember that by summer conditions. In the summer, we have high temperatures here, and you should be under very little pressure because you don't have schoolwork loading on you. So you're just relaxing, you got low pressure and you got high temperature. But you need to know why as well. So when we have a low pressure, then we generally have a large container volume. So the larger the container, the lower the pressure would be. If I have a large container, here's my gas, I have 2 gas molecules. The volume of those individual gas molecules is going to be very, very small compared to the container size. But the smaller the container gets, the more that volume actually does matter of the gas molecules. Also, the smaller the container, the more attraction or repulsion those molecules will have because they'll be closer together. And finally, high temperature molecules are more ideal meaning they follow KMT because they're moving so fast and rapidly that the effects of intermolecular attractions aren't going to be very important. They don't have time to attract each other because by the time they get close to each other, they move past each other again. So high temperature molecules are moving too fast to form attractions. If the gas is at the same conditions, then we can look at the gas themselves. So if volume, pressure, and temperature are the same, then we look at the gas. The smaller the gas particle and the smaller the IMF, or intermolecular forces, the more ideal the gas is going to be. For the same reasons as before. The smaller the gas particle, the more true to it having 0 volume it is. The smaller the IMF, the less attraction or repulsion it would have with each other. So on here it says, which is more ideal? Well, first I'm going to look at size. Neon and xenon are both noble gases. Neon is much smaller, therefore it's going to be more ideal. It also has the lower IMF because it has less electrons. H2S and NH3, you may remember NH3 is hydrogen bonded while H2S is dipole-dipole. Well, H2S is a weaker intermolecular attraction, therefore it's going to be more ideal. So go ahead and pause the video and figure out which is most ideal in each set. Restart when you have an answer. So on this first one, the thing that's different is temperature. Most ideal is high temp, low pressure. Since I want the more ideal, the helium at the higher temperature would be more ideal. For argon, it's the pressure. I want low pressure, so argon at 200 torr must be more ideal. And in the last example, they're at the same temperature and pressure, so I look at the gases themselves. Water, you should know hydrogen bonds, because that was our main example. And CH4 is nonpolar, so it was just LDF. So CH4 is going to have weaker attractions, therefore it's more ideal. Diffusion is the mixing of gases. Gases diffuse across a room to fill the entire room. If I spray perfume on one side of the room, it's going to eventually make it to the other side of the room. Effusion is related to that, but it describes the passage of a gas through a tiny chamber or through a tiny hole in a vacuum chamber. So the rate at which the gas goes from one side to the other side. So effusion is more of a quantitative value. It has a numeric piece to it. So the only thing you have to know about effusion is the rates of effusion to two gases are inversely proportional to the square roots of their molar masses at the same temperature and pressure. That boils down to the smaller the molar mass, the greater the average velocity. So if it says which of these two gases has the greater average velocity or has the greatest velocity or will be moving at a greater rate, the smaller the molar mass. Light things travel faster than heavy things. So given two gases, neon and carbon dioxide, they're at different temperatures, are in the same 2-liter container. Go ahead and pause the video and answer these two questions. Restart when you have your answers. So for the first one, it says kinetic energy. Kinetic energy directly related to temperature. The higher the temp, the higher the kinetic energy. So since CO2 is at a higher temp, it must be the one with the greater kinetic energy. So make sure you make note, if you missed it, that it was at the higher temperature. Rate of effusion, we're looking at molar masses. The smaller the molar mass equals the greater rate of effusion. Since neon has a molar mass of 20 and CO2 is 44 grams per mole, neon has the greater rate of effusion. You'll need to be able to read a graph like the following. These are referred to as Maxwell-Boltzmann distributions. They look a little complicated, but they're not. So we see the same gas at 0 degrees, 25 degrees Celsius, and 100 degrees Celsius. We have the probability of a gas at that kinetic energy On the x-axis, we have kinetic energy. As the temperature increases, the probability of molecules having a higher energy obviously increases. So it says drop a vertical line from the peak of each of the three bell-shaped curves. That point on the x-axis represents the average velocity of the sample at that temperature, or it should actually be the average kinetic energy of the sample at that temperature. So at 0 degrees, 25 degrees, and 100 degrees. Notice 100 degrees has a greater average kinetic energy. That makes sense. Notice that the 100 degree graph is the flattest. The area under the curve must remain constant. So in order to have more of the kinetic energy over on the right-hand side, it's got to get flatter or squattier. The lower the temperature, the higher up it's going to be. So that throws people because they think, oh, the high temperature should be the one that's really high and pointy. No, the highest temperature is always going to be the flattest one. Lowest temperature is always the one that is more rounded or more towards the left. So on here, go ahead and pause the video. These are types of questions that you could see. Go ahead and answer 1, 2, and 3. Restart when you have an answer. So the highest temperature should be the lowest, which is D. Notice it's got the highest kinetic energy. Which gas is at the lowest temperature? Lowest temperature, the highest up, so that would be A. And what is the average molecular speed of B? So I'm just going to drop it down at the highest point, and that's around 500 meters per second. You can see this with temperature. You also could have solved this with Graham's rate of effusion. Another way that you could have seen this question worded is if I said match A, B, C, D to helium, neon, argon, and krypton if they're all at the same temperature and they're all in the same container or same size container. Well, helium, I know, has the lowest molar mass, so it should have the highest velocity. So that would mean that this one must be D. Neon has the next to lowest molar mass, so it would have the next highest velocity of C. Argon would be B, and krypton would have the lowest velocity because it's got the greatest molar mass. It would be the slowest. So you'll see these graphs saying identify which element or compound would correspond to each, or maybe saying which temperature is the greatest. And finally, you could have a question where they give you 1 or 2 of those humps and then say, what would happen or show on the graph, what would a picture look like if I increase the temperature or decrease the temperature? Again, the area under the curve should remain constant or pretty close to the constant. So notice when it gets flatter, it also goes to the right more. I can't just have a graph underneath another graph, because the area under the curve wouldn't be the same. And finally, when HCl vapors mix with ammonium vapors, a solid ammonium chloride ring forms. What letter would best represent where the ring would form? Justify your prediction. So go ahead and pause the video and figure out where that would form. So what you should have been thinking was HCl has a molar mass of around 36 and NH3 is around 17. Since NH3 has a smaller molar mass, it's going to move faster than HCl will. Therefore, it's going to travel further than HCl will before they meet. So A is our correct answer. B would be if they were roughly the same molar mass, and C would be if HCl had the smaller molar mass. So NH3 will have a faster average velocity due to it having a smaller molar mass. It will travel further than HCl before meeting.